Good morning, students. In the previous lecture, we discussed about the deterministic finite automata, that is DFA, having 5 tuples Q, sigma, delta, Q naught, and F. So, delta is the transition function, as I already told you. So, today we will discuss the extended transition function, that is delta star. So, what is the role of extended transition function? Right. So in this lecture, we will explain the detailed example of extended transition function. So extended transition function is nothing. It is just like the transition function having more than one inputs on the present states. So let's see the example step by step. For example, in this case, Q0 is the present state and AB is the input. So first of all, we will apply A on state Q0, then apply B on the outcome state. And finally, we will reach on Q2. So Q2 is the final state or the output state. Let's see with the help of the diagram also. That diagram is the transition diagram. In this diagram, Q0 on state Q0, we are reading symbol in A, and now we are reaching to state Q1, and on Q1 state we are reading the symbol or the input symbol, that is B, and finally we are reaching to Q2. So this phenomena can be considered as the extended transition function. The same example can also be considered for extended transition function, that is Q0 comma ABBA. In this case, first of all, we will apply A on Q0 state. We are moving to the Q1, and on Q1 we are reading our next input symbol, that is B, moving to the Q2 state, and then B again, then we are moving to Q3 state. Now on Q3 state, the last input is A. So on Q3 state, A, if we are reading state input A, finally we will reach to Q2 state. So this phenomena is considered as the extended transition function. So next example is simple example of finite automata. In this example, Q0, Q1, Q2, there are 3 states, and overall inputs are, that is sigma equals to 0, 1. So if we want to write the whole components of that finite automata, like number of states, initial state, final state, or the accepting state, input alphabet, whatever. So these symbols are represented by using this diagram as number of input alphabets 0 and 1. So we can write here sigma equals to 0, 1, right? And total Q is the final set of states. So total number of states are Q0, Q1, and Q2. There are 3 states in this diagram. So we can write here Q0, Q1, and Q2. And as I already told you, that initial state is Q0. Initial state always will be the single state. So here Q0 is the initial state, and final state is represented by 2 concentric circles. So here in the given diagram, Q0 and Q1 are the final states or the accepting states. So you can write here final state F is equals to Q0, Q1. Is it clear? So with the help of this finite automata, with the help of this diagram, we can write all the tuples represented in this represented as per the diagram. Now one more thing, that is the transition function. We can represent it by the transition diagram, as well as transition function, as well as transition table. So the transitions can be represented in this table. That table is called the transition table. So how this transition functions can be represented in the form of table, we can see here total number of states are suppose 3, right? Q0, Q1, and Q2. So write the number of state here, Q0, Q1, and Q2. And total number of inputs are 0 and 1. So write the input here 0 and 1. Now see in the diagram, on input 0 from Q0, you are moving to the self, you're moving to the Q0 state. So on input 0, you are moving to the Q0. On input 1, you are moving from Q0 to Q1. So write on input 1, you are moving to Q1, that right, you have to write here 1. On Q1, input 0, you are moving to Q2. On 1, you are again on the same state, that is Q1. So write here Q2 and Q1. And the last state, that is the Q2. On Q2, if you are reading input symbol 0, again you are in Q2, or if you are reading input symbol 1, then again you are in Q2. So in this case, in both the cases, you are on same state, that is the Q2. So the same thing, all the tuples of finite automata can be represented with the given diagram. Now, suppose another example of finite automata. In this example, there are two states. You can see here, because states are represented by the circles. So in this example, there are two states. The states are off and on. And initial state is off state. Because why it is initial state? It is the initial state because it is represented by circle as and an arrow. So this state will be the initial state. And this on state is represented by two concentric circle. That's why this state will be the final state. Okay. So it is the simple representation of the finite automata. Is it clear? Now, what sequence of F lead to the final state? Suppose I want to ask you a question. What sequence of F lead to the final state? It means that कि हम इसमें कितने F को रीड करेंगे जिससे हम फाइनल पे जाएं. फॉर एग्जाम्पल, जस्ट वी विल स्टार्ट फ्रॉम दिस ऑफ स्टेट. नाउ वी रीड F, एक सिंगल F हमने रीड किया. वी आर मूविंग टू द फाइनल स्टेट. एंड अगेन वी आर रीडिंग अनदर F. वी आर मूविंग टू द ऑफ स्टेट. And third F we are reading, then we are moving to the on state. So it means that अगर मैं एक F रीड करता हूं ऑन स्टेट, दूसरा रीड करूंगा ऑफ स्टेट, तीसरा रीड करूंगा ऑन, चौथा फिर ऑफ, पांचवा क्या होगा? ऑन होगा. इसका मतलब क्या होगा कि जब भी मैं ऑड सीक्वेंस को रीड करूंगा, किसमें? F को ऑड सीक्वेंस में रीड करूंगा, इन दिस केस द मशीन विल बी ऑन द फाइनल स्टेट, राइट? So this is the simple example of finite automata or deterministic finite automata. Now, next point is the language of DFA. What about the language? So the language of DFA is the set of all string over input string starting from Q0 and following the transitions as the string is read left to right will reach some accepting state or the final state. So we will take the previous example. In this example, we are starting from initial state, that is off state, and we are moving to the final state, that is the on state. So in this case, how can we write the language? So always we will write the language for the accepting state, right? So in this case, अगर मैं एक F को रीड करता हूं तो मैं कहां जा रहा हूं? फाइनल स्टेट पर. दूसरे पर नहीं जा रहा, तीसरे पे फिर फाइनल पे जा रहा हूं, चौथे पे नहीं जा रहा, पांचवें पे जा रहा हूं. इसका मतलब क्या हुआ कि पहला F, एक F होगा, एक्सेप्टेड स्टेट में पहुंचेंगे हम लोग, क्योंकि एक F को रीड करने के बाद हम लोग कहां जा रहे हैं? फाइनल स्टेट में. फिर दूसरे पे नहीं जा रहे तो दूसरे को इन्वॉल्व करने की जरूरत नहीं है, क्योंकि हमेशा हम लोग लैंग्वेज जो लिखेंगे वो किसके अकॉर्डिंग लिखेंगे? एज पर द फाइनल स्टेट, राइट? तो दूसरे पे नहीं जाएंगे, थर्ड वाले पे हम वापस से कहां पहुंचेंगे? फाइनल पे. चौथे वाले F पर नहीं जाएंगे, पांचवा वाला F रीड करेंगे तो कहां पहुंचेंगे? फाइनल पे. इसका मतलब फर्स्ट एक F आप रीड करो तो, 3 F रीड करो तो, 5 F रीड करो तो, 7 F रीड करो तो, you will be on the final state. So how can we write the language for such type of DFA? So in this case, we can write here F to the power n, means F to the iteration of n. Here n is not the power, actually it is just like the iteration. It means that if we iterate n odd times, then we will reach to the final state. So this type of problem can be considered as the language of DFA, deterministic finite automata. So these are the various examples for you to practice to find out the language of these finite automata. Now we can apply certain rules, the explained rules, to design the finite automata or to construct the finite automata. Clear? So in this example, suppose it is given that design a finite automata with sigma equals to 0 comma 1 accept only input 1 0 1. It means that sigma equals to 0 comma 1 means there are only two symbols used in the finite automata, and the restriction is you have to design the finite automata that accept only 101, right? So in this case, the very simple example is this one. So in this case, just 101 means you are start with the initial state, read the symbol 1, move to the another state, then read the another symbol that is given to you 1, and finally after reading the last one you have to move to the final state. So simple diagram can be represented as q0 1, move to q1, and then 0, just move to the q2, and 1, finally move to q3. So this is the simple example. Now the next example is, suppose the set of all string sigma equals to 0 comma 1 ending in 0 0. It means that the ending must be by 0 0, two consecutive zeros minimum, right? And initial starting may be 1 or 0, whatever. So in this diagram we can see very clearly, start if we read 0, then just we are moving to q0 state, we remains on the q0 state, and if we read 0, moving to the q1 state, and another 0, we are moving to the q2 state. So start with the skeleton. So just we can draw the skeleton like this, 0 and 0. You have to read, you have to require 0 0. So in this case, start with initial state, on 0 input move to the next intermediate state, and another 0, you are moving to the final state. So this structure is called, the basic structure is called the skeleton. And now we apply the other restrictions here. Of if suppose there are 3 zeros, in this case we are moving to the in this case we are in the final state. So on 0 we are in the final state, that is q2. So put loop in this state q2, and then suppose the condition is the input is 0 0 1 0 0. So in this type of string must also be accepted by the given finite automata. So in this case, 0 and 0 we are moving to q2, and 1 we are moving to q0 again, you can see here, and 0 0 means 0 and 0. So after completing the string we are on the final state. So this string is accepted by the given finite automata or constructed finite automata. So this will be the final machine or DFA for the string sigma equals to 0 comma 1 ending with 0 0. Some other example can also be explained like constructed DFA that accept the language 0 1 0 comma 1. In this case there are two ways. The two ways are, after reading 0 1 0 your machine will be in the final state, first one, and another one is after reading only 1 your machine will be the final state. So we have to write two paths actually. One path is after reading 1 your machine will be the final state. So in this case start with q0 or any other state, name of any other state. So after reading 1 we are in final state, and this second case. And first case is after reading 0 1 0 your machine must be in the final state. So in this case just we draw the skeleton as I already told you. In this case start with 0, then 1, then 0, and you are moving to final state. And after this is the dummy state, because in this state you never reach to the final state. Means accepting state is this, having the two paths, that is the 0 1 0 or 1. So this type of construction can be done with the help of this diagram. And now the next point is sigma star and sigma plus. What about this sigma star and sigma plus? So this is very simple and very important for the examination point of view. The sigma is any alpha weight, sigma equals to bi, for example. In this case, this bi is the input alpha weight, right? If we apply sigma star means set of all string including null, or obtained by concatenating 0 or more symbol from sigma. For example, if I take sigma equals to y, then if I want to ask you what will be the value of sigma star? It means any combination of y including null. That means null by any combination, by triple times y, four times y, and so on. So in a sigma star is nothing. It is just a set of all string including null, while sigma plus is the same thing except the null condition. So the definition of sigma plus is the set of all strings excluding null or obtaining by concatenating one or more symbols. So let us take the same example here. If sigma equals to y, in this case, sigma plus will be by, comma, by, comma, by, means start from by, but in case of sigma star, it will start from null. So this is only the difference. I repeat the same difference again. In case of sigma star, we write all the possible combination including null, while in case of sigma plus, we write all the combination excluding null. So only this is the difference between sigma star and sigma